All right, hello everyone. Welcome to the Kirby Institute seminar series today. My name's Richard Gray. I'm the head of the Mathematical Epidemiology and Evaluation Research Group here as part of the surveillance program. To begin the seminar today, I would first like to acknowledge the traditional custodians of the land, the Bidjigal people of the Aurora Nation, and pay my respects to elders past and present, and extend that respect and acknowledgement to any Aboriginal and Torres Strait Islander people joining us today. So today for my seminar, it's a pleasure to welcome back Kirby alumni. Some of you may remember Robyn from 10 years ago, it turns out. So Robyn completed her PhD at UNSW in maths department and then came across to the Kirby to do some mathematical modelling with us in 2014. She was part of David Wilson's program at the time and did a lot of work with the World Bank and developing the HIV Optima model and applying it in many countries of the world. But at the end of 2014, Robyn left us and decided to go to sunny and calm Copenhagen to become an academic and essentially take on a lecturing position and train future modelers, I suppose, in some ways. Throughout that time, Robyn's been developing models and working with the World Bank and also the Gates Foundation. And so she came back to Sydney in 2022 with her young family and has continued working with the Gates Foundation as a contractor and has decided to come to Kirby again to see us all and give us a presentation on her latest modelling work with Starsim. So over to you, Robyn.
Great. Well, thank you for the introduction to speak today, and thank you, Richard, for the introduction. I too would like to acknowledge the Bidjigal people of the Eora Nation and pay my respect to the elders past, present and emerging, and extend that respect to any Aboriginal people in the room with us today. So I'm here today to talk about a modelling framework that I've been working on over the past couple of years. If you don't have time to stay for the whole seminar, I wanted to give a kind of, a kind of poster version of the entire seminar in just this one slide. So I'm going to be talking about an open access modelling framework for making agent-based models of multiple different diseases. And we've called this framework Starsim. This is kind of like star as an asterisk, which is like a wild card if you're searching for text strings and that kind of thing. So the idea is that you could put any disease you want here and use it to simulate that disease or multiple diseases. So one of the key things that I want to emphasize in talking about this framework today is that it's designed to be easy to use. And we've trained a lot of people so far, about 200 up to today, in how to use the model. But this is also a very collaborative, ongoing, and still in development project. So we're kind of actively seeking people who might want to get involved with modeling questions related to particular diseases or policy questions. So please do get in touch if you have any questions about any kind of modeling work that might be relevant for this. Then over on the right-hand side, I've put some links. You know, if you're kind of multitasking with multiple tabs open, like most people generally are in these seminars, then you're welcome to have a look through those. There's the code bases for all of the different model frameworks that I'll talk through today. And then also some links to, or some references to some of the papers where we've published descriptions of these models. Okay, so that was kind of the flyover version. Now going into the kind of details of the talk, I'm going to start with a bit of a motivation and a genesis of how and why this Starsim modelling framework came about. It has origins in the pandemic and was thereafter expanded to other diseases and health areas, and then relatively recently has evolved into a standalone independent framework. So I'll talk through those kind of history steps because they give a lot more context for what kinds of questions this modelling framework can be applied to. And then I'll talk a little bit about some of the design and implementation features of the modelling framework itself, kind of taking a more software architecture approach, and then quickly look at an application of modelling co-circulating STIs. I'm happy to take questions as we go. I'm not sure what the kind of standard thing is, but just jump in if you do have anything. Okay, so this is the genesis of this model. So it was initially developed by the Institute of Disease Modelling, which is an embedded research group within the Gates Foundation. I've been working as a contractor with the Institute of Disease Modelling since the beginning of the pandemic. The role of that group is, well, it's kind of three primary functions. One of them is to provide internal modelling support to questions that might emerge from within the Gates Foundation about how they should make decisions. A second function is to conduct independent scientific research. And then the third key function is to develop open source modeling tools. And it's that kind of role that I want to focus on today when talking about this particular modeling framework. So in March 2020, there was a kind of, rapidly emerging urgent need for fast-paced modeling tools. A lot of modeling questions were coming up, and it was, kind of the existing set of models that the Institute of Disease Modelling had were not kind of fast enough or nimble enough to be able to adapt to these rapidly emerging questions. So around that time, March, April 2020, we developed this new set of tools in order to be able to model at a kind of pandemic pace. This model that was developed for that purpose was called COVASIM, short for the COVID-19 agent-based simulator. It's an agent-based COVID-19 model which was built to explore complex scenarios. Now, a lot of what it was designed for was to have simplicity, but also flexibility, because a lot of the questions in the early stages of the pandemic were changing. So I'll go through some examples of that later. But then the idea of it being like very kind of easy to use was also meant to be so that people, not just the people who had developed the model, but also other people would be able to pick up the model and use it for their own modeling questions. So there were, as you, I'm sure, no doubt recall, many questions that kind of emerged throughout the pandemic. And I'll just put like a quick timeline here from the sort of onset of the pandemic moving through to the later stages. In the initial stages, a lot of the questions were around like what could be done to lift lockdowns that were imposed as a kind of emergency response. A lot of questions around testing and tracing levels that would be required in order to go back to a state of full mobility. So this was one of the first applications of the COVASIM model, looking at different levels of testing on the x-axis and tracing on the y-axis that would be required in order to keep the R effective value lower than 1 in a scenario where the lockdown had been completely lifted and the society had returned to full mobility. So these kinds of questions were obviously like one of the first things that were put to modelers in the early stages of the pandemic to be able to look at questions like this. So this is one of the first things that the COVASIM model was applied to. Then moving into the kind of Northern Hemisphere summer, there were a lot more questions emerging around what should be done with schools, which had remained closed for the majority of the kind of first wave of the pandemic, which is that kind of first little bump there. And then the questions were around what degree of precautions would be necessary in order to continue, in order to reopen schools safely. So this was one of the next applications of the COVASIM model, was to look at questions like this. Again, these simulations are looking across different levels of tracing and testing in order to understand what levels of testing and tracing would be necessary in order to curtail any future waves of the pandemic. There were also questions around reopening borders. Some of this work, this work here is from Vietnam, but we also did a lot of work in Australia looking at these same questions. What degree of testing would be required within the society as a whole in order to make sure that if there was a new case that sort of got through quarantine and emerged into the society, what degree of testing would be required in order to kind of to identify that fast enough that, again, that outbreak could be quashed effectively. And this, I mean, I found this quite interesting from Vietnam, that even So reopening borders, there would be very large outbreaks unless symptomatic testing would increase substantially. So in all societies that were kind of maintaining a COVID zero policy, there was generally lower levels of symptomatic testing because there was, less identified risk that people had. So that meant that the risks of substantial outbreaks was significantly higher than in cases where you might have had higher degrees of symptomatic testing. And then moving sort of forward, as we kind of entered the second year of the pandemic, a lot of the new questions were emerging around the impact of new variants and different vaccination rollout strategies. And so again, this was a point where like the development of the model had to change in order to track the new scientific information and the new policy questions that were emerging. So when we initially created this model, it didn't have reinfection, it didn't have multiple variants of concern. And these were all adaptations that had to be made in light of this kind of ongoing development throughout the pandemic. Anyway, so that's just a little bit of background. Then as the as the COVASIM model was developed and released as open source modeling, it spread relatively quickly throughout the world in terms of collaborators and people who were making use of the model. And this map shows, the stars show different locations of collaborators that we were working with throughout the pandemic, who were using COVASIM to answer policy questions for their contract. So, I want to then kind of segue into, as we were kind of developing this model and seeing relatively high uptake of this modeling framework in terms of collaborators and so on, the next kind of follow-on question that we had was whether the general structure and principles and design and philosophy of this modeling framework could be adapted to other diseases. So, in thinking about what that structure looks like, it's an agent-based model, which means that it simulates the state of individual people or agents over time. And the fundamental calculation is to figure out the probability that a given agent on any given time step will change from one state to another, whether that's from susceptible to infected via a transmission event, or whether they get diagnosed or die or have any other kind of change of state. So this is the fundamental thing that agent-based models do, is to track agents and then track the sequence of events that happens to them over time. And then the way that transmission happens is that all of the agents are connected over a network, which is then how people can infect one another. So that kind of fundamental agent-based modeling structure seemed like something that would be transferable to other disease or health areas. I mean, obviously we didn't invent agent-based modeling. I don't want to kind of, this is, just to use the same kind of like principles and design that we were using for COVASIM, and then to translate that over to other diseases. So this is a kind of, I guess, like a roadmap of how we then went from that initial model COVASIM for modeling COVID-19 to the next kind of, the next disease areas that we started to look at with the same kind of framework. We moved, our first step was into HPV, human papillomavirus, and sequelae of cervical cancer, as well as family planning, which is what the FP-SIM stands for, and synthpops, which is kind of general population modeling for demographics and so on. So all of those 4 models were kind of developed in the past couple of years and have since been released and published. And we have sort of several ongoing applications looking at applications of using these modeling frameworks in different contexts to answer policy questions. But then we were also interested in kind of taking this and developing it into more disease areas. And so we started working on polio sim and STI sim and RSV and tuberculosis and typhoid, several different kind of disease areas at once. And I guess the graph on the right-hand side here is designed to show that as we were kind of developing all of these initially kind of in parallel to each other, there was a significant amount of like code that was shared between the different models. A lot of the kind of basic infrastructure that you need in order to create an agent-based model doesn't depend so much on what disease you're modeling. You're always going to need to create a population of agents, figure out some way to have those agents interact with each other, and then track different events that happen to them over time. those kind of fundamental things don't depend on the disease at all. So the next thing that we wanted to do was kind of think about how we could create a more unified version of this, whereby all of that code that was shared across those different code bases could be lifted up into one kind of unifying architecture that would then enable people to develop new disease models relatively quickly, because they wouldn't have to do all of that basic work of like building up all of that architecture from scratch. Okay, so that kind of led us to this idea of developing a Starsim model, which would contain all of that architecture so that the individual diseases could be slotted in relatively quickly. So I'll talk a little bit about some of the design and implementation. Yeah, so we kind of started out with this minimalist approach, which was kind of what was depicted on that previous graphic, that we had a set of design principles that anytime that one of our kind of team was developing a new model, they'd say, okay, I'm just going to take the general idea of how these other models were built, and then use it to design my model. But as we realized how much of that code ended up being shared, then we thought perhaps there should be a kind of more maximalist approach, which would consist of a single unified code base, so that you would just have one kind of overall set of code, and then everything would be kind of embedded within that one thing. We're now kind of like somewhere, we ended up landing somewhere in the middle here, in this kind of what we're calling intermediate architecture approach, whereby what we want to design is a set of interlocking modules, so that the kind of overall idea is that there's a framework that allows you to piece things together, but the individual things that you're piecing together, you have a little bit more flexibility over. So they're not quite as rigidly defined as what they would be if you were in the maximalist framework. So over time, we kind of changed perspectives on this. We were originally, as I said, kind of thinking towards this maximalist thing. About a year ago, we were kind of more in the minimalist world, where we had these different, completely independent code bases with a lot of overlapping code for COVID-19, for HPV, and for family planning. And where we are now is, as I said, kind of in that intermediate zone of thinking about how we can unify these different code bases without making it too rigid and formulaic about how you use them. Okay, so here's a kind of like schematic showing the I guess, idea of how this Starsim modeling framework is supposed to work. And the main takeaway I want you to get from this graphic is just that there's different colored boxes, really. So there's a kind of overall big gray box, which is your simulation. And then as you're designing what exactly you want to model, you decide which of the other boxes you want to put into your simulation. You're pretty much always going to want to put people in the big blue box. This will keep track of people who are alive, who are their age, their sex, other attributes of people, like whether or not they've been vaccinated and that kind of thing. All of that would be contained within your sort of overall people. Then you would have some details. If this is an infectious disease that you're modeling, then you might have some details about how those people are connected to one another so that you can track transmission. So, you could have sexual networks or respiratory type networks, injecting networks, environmental networks, or custom networks, depending on exactly which infection you were modeling. And you can also use the same kind of Starsim architecture without the networks. So again, this comes down to when you're building this and you get to decide which of these boxes you want to put in. So if you wanted to model a non-communicative disease which didn't have any network transmission, then you could just leave that aspect out and then continue to model using the same kind of code base and architecture. Likewise, you might decide that you want to include demographics within your model because you're modeling, say, flu over 5 years or something, or you might decide you don't need to because you're modeling an outbreak within a prison and you're only simulating over a few weeks or something. So there's different choices that you could make in order to kind of throw these things into the simulation box or not. And then one of the most important things that will differ from one simulation to another is which diseases you decide to include. Whether you want to include, I've just included like a handful to illustrate the idea here. But the idea is that you could kind of write your own and all you would kind of have to do is specify like the overall kind of structure that the disease was going to follow, whether that's a susceptible, infected, recovered type structure, or whether it's you're capturing different sort of sequelae as people move through stages of infection. You can kind of just put those details in, and then the rest of the Starsim architecture would handle the details of how to make people transition from between those different states, and how to handle transmission and that kind of thing. Another kind of important element here is in this connectors box. This is where we can, I've got an illustration of this later in the talk, but this is where we can put in details that allow us to capture the fact that conditions are not necessarily independent of one another. So for example, the example that I'll show later is looking at HIV and syphilis in a co-transmitting model. And we know that people with syphilis or active syphilis are more likely to transmit HIV. So we can capture and acquire HIV. So we can capture that kind of disease interactions within these connectors. Or if you're modeling things which co-transmit in similar populations but don't necessarily elevate the relative risks of each other, then you could have the same network and two different diseases transmitting across the same network without necessarily needing to model any connectors between them. Then there's, in many cases, you would often be including interventions. Analyzers are things that you could then say that you want kind of custom results printed out from the model. And then you've got your sort of typical set of results. So all of these things would be kind of thrown into a simulation in a kind of mix and match modular fashion in order to capture what you wanted to model. I want to just briefly talk about the kind of vision for Starsim. So this is, I mentioned that this is kind of, that these models are coming out of the Institute for Disease Modeling, who, a lot of the, I guess, strategy for that particular group is to promote quantitative decision-making in a very kind of open access and collaborative way. So this kind of user-centric approach to software design is really kind of one of the fundamental principles that's underlying Starsim and also all of the precursor models like CovaSim and HPV Sim and Family Planning Sim. So this user-centric approach has a few elements that I just want to touch upon. I mentioned previously that one of the key facets is that we want things to be kind of simple and intuitive and accessible so that it's easy for the model to be used. And that we don't want people kind of bogged down in like implementation details of how to do particular software things, which is, I don't know how many of the people here have tried to build models before, but often you get like really weighed down by it's things that you're like, surely somebody has solved this before. Like I shouldn't be sitting here coding up my own histogram as though nobody's ever written a histogram before. So as much as possible, if things that have been done before can just be easily pulled out and then you can just concentrate on the science, then that really makes the science a lot better. And, this is also kind of part of the, using a similar kind of logic, we wanted to make sure that this wasn't a tool that was going to be only accessible to highly trained, university academics. This should be something that could be run by people who are relatively new to coding without them having to kind of build everything up from the ground. And a lot of this also comes down to then a question of relinquishing control. This is, as we've kind of mentioned throughout open access software, we've had a lot of questions in the past when I've presented this work about like, well, what if somebody takes your model and produces results that don't seem credible? Like, would that be a problem? And having, reflected on that a lot, of course, I wouldn't want to advocate for bad science ever. However, I would say that it's also not optimal to be kind of necessarily gatekeeping the way that people are going to be using software. So I think the idea is to build good software and then trust the users to do good science with it. I'll talk now a little about the kind of design philosophy and going into some of the kind of software aspects itself. So I'm coming back to this idea of simplicity, and on the right here, I'll just even if you don't code or haven't never used Python before, these models are all written in Python. I think that the way that the code is written is fairly straightforward, right? So you import the package, CovaSim in this case, you create a simulation, you run it, and you plot it. So with those 4 lines of code, then you get these nice plots. So this is part of what going to the point I was making earlier, that you don't want to have to, like, if you're making your own model, spend all this time writing plotting code when really it's just, you just kind of want to run it and see what the results look like, right? So to have a lot of that kind of pre-packaged is one of the core goals here. So those kind of common things that people would want to do, we wanted to make sure that was really simple. So if you are running a simulation, you're going to want to be able to do that without having to kind of, do it all yourself. Similarly, if you want to change the parameters or bring in any kind of detail or specificity to that model, that should also be fairly easy to do. I mean, it was only 4 lines of code to run a simulation that kind of didn't use any data or like context-specific estimates, but people are obviously going to want to use those estimates, and that should be easy for them to add as well. So just to give an example, if you wanted to run that same model, but for like Vietnam instead of whatever that default context is, then when you set up that simulation in the second line of code there, rather than saying sim equals sim, then you would just put location equals Vietnam in there, and then it would automatically import all of the demographic and household contact data from Vietnam, and then you would be running the model with customized demographics and contact network. And then if you want to make additional modifications in terms of the ways in which people introduced interventions and so on, all of that is relatively straightforward to do as well. So all of those common things need to be simple, but then the flip side of that is that things that there's never two modeling questions exactly alike, right? So there's always some kind of customization or some kind of like little unique quirk about how people want to use their model. And we wanted to be able to make sure that it wasn't too difficult for people to kind of get around the standard workflows and set up their own unique workflows if they wanted to. So that leads us to the second point there, that uncommon tasks can't always be simple. Like maybe you would have to write a little bit more code, but it should still be possible to modify this in any way that you would want to in order to produce customized results. So that's kind of one of the main kind of design philosophies that we've stuck to. And then this next one, it kind of goes again into this question of simplicity and some of the design considerations that we were thinking of. So we wanted this to be a model for scientists and people who were going to be using it for policy questions. A lot of the time when modelers are creating models, and I say this as a dedicated modeler, so I'm definitely at fault here, then they're not kind of thinking necessarily about how much work it would be to modify that model and do other things. So in this kind of equation here, you can think of this as the total, if you're writing a piece of code as a modeler, the total amount of work that your code creates is equal to the sum across everybody who's going to use that model of how much ramp up time it takes, plus how many times they need to read each line of code and how long it takes them to understand each line of code, plus how many times they need to edit each line of code and how long that takes. Now, if you've only just got one person, then you don't care so much about all of those kind of multipliers and that sum at the beginning, because then you're only concerned about you and the time that it takes you to understand a line of code that you've written or edit a line of code that you've written is quite small. But as you start scaling up and having other people use your same code, then you need to think more about how to minimize that RP, which is which is how long it takes to read each line and how long it takes to edit each line. So we were very focused on, because we wanted this to be open access software, that question of how we could make it easy to understand and to modify. This section is very much tailored to modelers, because this is one of the things that we found, one of the biggest advantages and revelations in the early part of the design of this. So a lot of the time when you're running an agent-based model, you've got a whole series of different agents. And then at each point in time, so, you end up doing all of these loops. At each point in time, for each person, for each state, you have to make an update. Now, if you're running, say, for 2 years, a daily time step, so about 700 time steps with a population of about 30,000, and you've got 30 states, then you've got more than a billion updates that you need to do. So this is why these agent-based models tend to not scale particularly well, because it doesn't, I mean, that's a big number, right? So you end up only being able to run them for relatively small populations or relatively small amounts of time, or you end up running them for like a week while you are like on leave or stressed about your deadlines or something. So it's conceptually a simple proposition because it's simple what needs to happen, but it's very inefficient. So one of the main speed ups that we made early on in that's kind of how it would look in code to do it that way. One of the main updates that we made early on was this kind of arrayification idea, which is the same kind of idea. So on each time step and for each state, you update everybody. So it's a lot faster to work with these kind of array systems in most computing languages than it is to do that kind of a loop thing. And then that's how it looks in the code, but I just kind of want to focus on like how much of a speed up difference this makes, because even if you're not interested in using any of these kind of model architectures or frameworks, I think this is something that is quite useful and transferable to other models. So when we were doing it the kind of loop way, updating everybody on each time step, that's what you can see in the blue dots there, and it would take about 3,000 person years per second. That's how fast we could run it. And then the orange one, you can see that as you increase the population size, first of all, as you increase the population size from say 100 to 1,000, you don't really get any increase in terms of how long it takes to run the model, because you've just still got these arrays. So it doesn't matter whether it's an array of 100 people or 1,000 people. As you start increasing the population size more, it does slow down, but you're still at much, much, much faster speeds compared to when you're doing the loop approach. And there's an illustration of that here. So the left-hand side is doing the loop approach and the right-hand side is doing the array approach. And you can kind of see, just sometimes it's helpful to see how slow things are to understand how slow things are. Yep. So this was for the family planning model, and the one on the right, the array-based version, takes about a second and a half, whereas the one on the left, using the loops, takes about 17 seconds for this population size. Okay. So that was kind of, I wanted to talk through some of the implementation details and the genesis of the model. I also wanted to show you an example of how we've used the Starsim modeling framework to model co-circulating STIs. This is very much work in progress. I mean, I think I've caveated most of what I've said so far as being work in progress, and Richard assured me it was fine to come and talk about work in progress, but as long as you kind of keep that front and center of your mind as I go through some of these results. Okay, so just, a bit of background. Global burden of STIs, huge and increasing at increasing rates. Estimates, according to the World Health Organization, more than 1 million new STIs every day, including lots of affected pregnant women, leading to subsequent negative birth outcomes, and a lot of variation in terms of the burden by geography. So you can see on the the top, these are estimates of global STI prevalence by region. Somewhat out of date now, but nevertheless gives you an idea of the variation. And then also on the figure on the bottom part of the slide is showing that a lot of the burden is disproportionately concentrated in young people, particularly for chlamydia, gonorrhea, but then also for syphilis to a lesser extent. So lots of prevalent STI cases and lots of variation. So there are lots of policy questions, as I'm sure many of the people in this room would already be aware of. Some of the ones that I have personally been kind of thinking through recently are looking at improved syphilis diagnostics. Now, in these kind of policy questions, one of the messages that I want to pull out is why it's important to kind of answer these questions with a co-circulating STI model, why you might be able to get away with answering these questions using the model of just syphilis, but your answer would be strengthened if you also were modeling HIV. So in that first point, I guess the idea is that if you had improved ways of diagnosing syphilis, then you would be able to attain better syphilis control. But because syphilis is strongly associated with, has a higher risk, I should say, of HIV acquisition, then you might also lead to better HIV outcomes. So your overall impact in terms of the disability the DALY impact would be you would see more of an impact if you accounted for both of those disease factors. So then other questions looking at the optimal combination and timing of STI diagnostics and treatments to offer within antenatal clinics to minimize negative birth outcomes. There's a lot that could be done here in terms of considering cross-cutting interventions, particularly with things like dual HIV and syphilis tests and dual prevention pills for HIV and pregnancy. So there's a lot of kind of cross-cutting things that are already kind of encapsulated within the products that are available. So it makes a lot of sense to consider those questions within a co-transmitting model framework as well. Then there might be questions around transmission and prioritization of testing and treatment, which needs to capture transmission pathways and network effects. Another point that I haven't put here, but which I think is also important to mention, is that particularly for STIs, there's just not great data. I know we're all doing our best, but there's still not fantastic data in terms of how things transmit. So to the extent that you can put the data that you have together, you can really strengthen the inferences that you're able to make from a model. So if you're just fitting a model for, say, gonorrhea, then you might have a few gonorrhea data points. But if you're also fitting a model for chlamydia, then you can really narrow down which networks and which populations seem to make sense with both of those pieces of information. So it allows you to increase your data that you can use in order to calibrate the model, which strengthens the inference and allows you to make better use of the limited data that we do have. So yeah, some example policy questions there. And I've been looking at some of these questions recently using the Starsim model structure, but you know, I mentioned that there's this kind of overall big box and you can choose which things you want to put in there. So in this case, I'm picking out particular diseases from within the STIs, concentrating for the moment on syphilis and HIV. All of these are kind of user customizable. Whoops, went the wrong way. And then I put this into a kind of overall model framework that then I call STIsim, just because obviously we like to name things. But then STIsim looks after all of the different diseases, which I've kind of thrown in there, but then also the interactions between those diseases in terms of the relative risks and the cross-cutting interventions and so on. Okay, so this is, I mean, again, very work in progress, but just looking at an illustrative case here where I'm modeling syphilis and HIV together. Now, you know, we estimates around that the ballpark of 2.5 times the relative risk of HIV transmission for people with active syphilis infection. And there's also kind of evidence, some evidence back the other way that diagnosis of early syphilis carries a high risk of consequent HIV. So if we put the two diseases within the same model, but we don't account for those relative risks, so we're just kind of allowing them to transmit across the same networks, then we would see the lines that you can see here in orange. So you have a kind of slowly increasing syphilis epidemic and a slowly decreasing HIV epidemic. But then if we account for the relative risks, then the syphilis infections are increasing more and the HIV infections are increasing at a slower rate. So putting the co-transmission aspect in there captures a lot more of the nuance of how these things are moderating one another. It also allows us then to capture the effect of, say, improved syphilis treatment, or actually this is improved diagnostics and treatment. So you find more cases and then you treat them. And you would expect that if you were able to find and treat more cases of syphilis, then that would decrease the number of syphilis infections that you would see, which is what you can see in the top panel. However, we can also model the secondary effects of syphilis treatment on the burden of related diseases, which is what we see in the bottom panel there, that with improved treatment and identification and treatment of syphilis cases, we can also see a kind of quicker reduction in the number of HIV infections that we would see. Okay, so this is, like I said, just illustrative. I want to kind of go on now to some of the limitations and discussion points. One of the main ones is that I haven't, I just showed you some illustrative results here, but I haven't spoken about calibration or validation, which are really critical parts of turning a modeling framework into a model. I've been kind of trying to be careful throughout to refer to this Starsim as a modeling framework rather than a model. It's a way that you can generate models, but it's not really going to be a model until you have calibrated it and validated it with context-specific data. So we have, because this is obviously a common thing that people want to do. So we have some built-in calibration methodology, but a lot of that, because this is still in development in early stages and so on, it needs to be put to the test more. As I keep saying, it's very much in development. Please get in touch if you think this could be interesting. I've spoke a lot about this kind of like underlying philosophy, which drove a lot of these practical user-centric design decisions. But again, this is something that we're still kind of refining and working on as we get kind of more and more users of the model. So the next phases, we've kind of been concentrating a lot for the Starsim modeling architecture on the initial development of the software and making sure all the pieces are in place and so on. But the next phases will really kind of move into applications of using this modeling framework in order to construct models and then use them for analyses. So I think that's basically my last slide. There's some links here this is the same links that I put up at the beginning slide, just if you're interested in digging into the code in any detail or looking through the methods papers. And then this is a very collaborative project. This is not the full list of collaborators, but just wanted to acknowledge that this has certainly been takes a village kind of an effort. So that's everything that I wanted to say. I'm happy to take any questions. Thank you.
Thank you, Robyn. Just in case you don't know, I'm not Richard. I'm Ben, but turns out Richard we should send him an apology because he actually got out of engagement. So I'll be taking over the Q&A session. So thank you, Robyn, for this very interesting talk about individual-based model. And I'm certainly interested because I'm also kind of modeling this kind of thing as well. So I will open up the Q&A session. And for those people who are online, feel free to put in the chat question in the Q&A box. Or if you're on the audience here, can go up to the mic and ask a question. So maybe I will start off with just some general question in this model in sense, what will be your big picture? I mean, the future progress, what are you trying to aim at? The main I guess I want to ask is, when you design a model, you design to what more model users or scientists kind of thing?
Yeah, that's a great question. So we've kind of had discussions going through different user scenarios, and I think there's different scenarios going from kind of relatively basic users who might just kind of use the model to run a quick simulation, and maybe those are people who are not modelers but just kind of want to get a kind of feel for a policy answer, and then going to intermediate and then very advanced modelers who might be using this kind of modeling framework in much the way that if you typically build models, you use many other kinds of standard modeling software like NumPy or whatever your chosen language is. There's a sort of standard set of packages that you would use. Epistem, there's like various options, and this could be like one of those options. So for people who typically build models as part of their work, they would be able to use some of this architecture in order to make that process a bit easier.
Yeah. No, that's fine. Yeah. Yeah, because as I know, there's many different type of models come between Python, C, whatever. Sometimes very focused on software side, and sometimes very focused on the scientific generating results type. So, yeah, it's many different approach, and there's pro and con each approach. I mean, you actually demonstrate an example there where you put in a model and then people kind of misuse it. Yeah, that's the thing. So I guess that leads on to the second question. So is there any recommendation when you're using a model? What should you do to make sure you're producing good science, not just random number generated?
Yeah, it's a difficult question. Yeah, I mean, so all of the models that we've published so far, like COVASIM and HPV and family planning, we've included a lot of documentation and tutorials, so that the idea is that people would hopefully be able to read this and understand best practice for how to use the model to generate sensible results. But I mean, as I said, it's always going to be possible to misuse any piece of software. So, there's only so much you can do in that respect. But I guess it's a kind of, assume no evil kind of thing that I think most modelers don't want to misuse their models to produce bad results.
I mean, one common practice in modern paper is actually open source. I mean, open your source code. And
well, exactly. Exactly. And I mean, this is the other thing. That's becoming much more common now, that in fact, a lot of journals require it, that if you publish a modeling paper, you have to publish your code as well. But it's a relatively new practice. And I think, we've all, I mean, anyone who's ever made a model, there's parts of it that you're like, oh, I'm not so proud of how that looks. Or, there's always parts that are a little tricky to get right. And having it all open access, I think, does a lot in terms of improving the science as well.
Thank you. Okay, there's one question from the mic there.
Right. Thank you so much. I actually have two questions. Sorry, I'm that person. But it's not a comment, it's actually a question. Thank you. This is fantastic. I really appreciate that. Getting to hear more. I have kind of, I guess, one kind of idea and one question. The first one is about kind of diffusion of information as a disease connector. So say if you say kind of like knowledge about a test or knowledge about some sort of intervention, how that might spread through a community, whether that could be applied. I guess that could be a custom disease state. So I think that might be really interesting for folks at Kirby to think about how can we educate kind of key connectors in a community and then see that information disseminate. And then the second one is the capacity to like ring fence people, to look at like migration within cities where people don't really move, but maybe one or two people move.
Yeah. Great. Love it. Yes. So with the first one, absolutely. We've had a lot of kind of thinking around this, and particularly in terms of like correlated heterogeneities and in terms of uptake of interventions. So if we don't capture the fact that people who are less likely to vaccinate are also less likely to test, then we would be dramatically overestimating testing rates, for example. So a lot of that is really important to capture. And then in terms of how that type of awareness of intervention or willingness to kind of seek care transmits, that's also something that we've talked about, having a kind of bespoke, in addition to the transmission network that allows the disease to transmit, the intervention transmission network, or what information dissemination network, you could also kind of add in to capture some of that. So we haven't done that yet, but I think it would be a really exciting application. And then your second question about, remind me.
Like migration or geographic.
Yeah. So I think there's a couple of different things that you could do there. Like if you wanted to kind of model like a particular outbreak, then you could just model a sort of contained subset of the population and then have, you know, some kind of new introduction or like new seeding of infections as people kind of came in from other more or differently infected areas. So we've looked at that. And then we've also kind of looked at like outbreaks within particular settings, like refugee camps and that kind of thing, and to what extent you would need to have particular vaccines stockpiled in order to curtail the transmission fast enough that it wouldn't then spread throughout the whole population and then beyond. So there's different things you could do there as well. A lot of that would come down to, like, you know, I talked about it's simple to do things that you want to do all the time. That kind of thing might be a bit more difficult because you might need a much more kind of customized network to capture that particular clustering among different regions.
Yeah, so I guess as a hypothetical, say you did HIV transmission in Sydney and Melbourne.
Yeah.
And so I guess you could it would just be built on your network connections rather than anything else.
Yeah,
So
yeah. It would be built on, exactly.
Okay.
Yeah.
Awesome. Thank you.
Yeah, sure.
Additional question, anybody? Well, if not, then I'll ask one more. That's of personal interest.
Okay.
Okay. You know, in many occasions, what we get in the data is not the perfect data. We got conflicts and it's sometimes too high, you know. And I guess that comes into the calibration process. So I'm just wondering what your recommendation if you got two set of data that doesn't fit in properly, what should you do?
Yeah, throw one out. No, I don't know. Yeah, this is very true. This is this is what makes calibration very difficult. I think it depends. It's a case by case thing, right? Like sometimes you can kind of take different calibration approaches that account for some of the relative uncertainty you might have in some of those data. So you might care more about fitting the one that you are relatively more certain about. And, you know, I guess there's various Bayesian methods for incorporating that kind of prior knowledge. But yeah, I think this type of modeling framework doesn't have a better answer than what the field generally has for that.
Yeah. Okay. We got one more question online. It's basically saying, let's see, health economists working with infectious disease modelers and looking at broader impact of intervention, I guess. Yeah. So do you have any particular challenges merging your work with health economic models?
No, I think we've often worked with health economic models. I mean, this type of modeling framework doesn't do costing or anything like that, but it does do estimates of impact in a baseline scenario versus a different intervention. So you can kind of get that part of the equation. And it also produces estimates of resources used. So number of tests or vaccines or whatever else, or health system use in one scenario versus another. So if you have costing estimates, you can kind of piece all of that together. Yeah.
Question there.
So very interesting talk. So I'm very interested in your method as well. But there's one question about the calibration method. So will you expose your your algorithms to other people so that we can do calibration? Because for the Bayesian calibration, a lot of software package they actually include like ordinary differential equation directly into the package. So it's really easy to do that. So if you can just do that, then it's really easy.
So, yeah, for sure. So what we have done is when you run a simulation, if you also have uploaded the data, then there's a method built into the framework for calculating goodness of fit, or different definitions of goodness of fit. So you could say, you know, I want to calculate mean absolute error or mean squared error or whatever. So whenever you run a simulation, it will produce that number for you. So that means you can feed it into any kind of like off-the-shelf optimizer that will then, you know, do its general thing of running something in order to minimize something. So it kind of automatically is plug and play with a lot of pre-existing algorithms. But then we've also built one in, it's called OpTuner. It's a hyperparameter optimization. Honestly, when people are like, why that one? I'm like, well, it just had nice like APIs. Like, I don't know, it was just easy to work with. But it works quite well. So for that one, we typically run like maybe 5,000 trials. And it works quite well as long as you don't have more than, say, 10 parameters or something like that. So then if you want to just use that one that's kind of built in, then you just kind of say, you know, sim.calibrate, and it will come up with those parameter estimates for you. But then for people who want to do kind of things that are more bespoke, or they have like different, you know, people often have preferences for how they want to do their calibration to work with an existing framework, and then they can use one of those existing ones.
Sorry, another calibration question.
Yeah.
Because I wonder if you include a lot of disease in your model, it will be more complicated to calibrate as a, like, you know, I'm a modeler, but if non-modeler wants to use it, do they have a freedom to which calibrate, like to give a priority to match which disease first and then maybe next one and the other one?
Yeah. I guess I'm not sharing anymore, but so with that HIV syphilis model that I was showing before, the model, when you run it, you get estimates of the prevalence of syphilis, prevalence of HIV. Let's say that you also had data on the prevalence of syphilis and the prevalence of HIV. So when you created the model, you'd upload that data file. And then when the model calculated the fit function, it would weight both those things equally. If you want to provide a different weighting, then that's just one of the inputs. So you could say, I care twice as much. You weight the syphilis data twice as high as the HIV. And then that would go into that automatic calculation of the goodness of fit. Now, you might also want to write your own unique goodness of fit function that weighted different data points at different times differently. You could also do that, but then you would have to kind of write that yourself.
Calibration is probably one of the hardest things to do during modeling. So
yeah,
any good approach will be keenly.
Yeah.
Any other question? I don't see any more question online, and no more for me. No one for. Okay. In this case, I just thought.
Yeah, you got my cold. I'm sorry.
Okay. I would just like to thank you, Robyn, for her presentation. Very informative and just and cool.
Thank you.